So far we've considered liquid-liquid equilibria and gas-liquid equilibria. Here we're going to consider liquid-solid equilibria. All right, first let's talk about things going into solution. So for example, we can write, if we have some component, say A, which is a solid, that will be in equilibrium with A, which is now solvated. And remember, if you have ions, for example, say NaCl, and that's in equilibrium with Na plus, and let's put it in aqueous solution, so the solvent is water, and Cl minus, aqueous. We treat this introductory chemistry level. Ksp is a concentration of sodium and the concentration of chloride minus, and that's the equilibrium constant for this reaction, and we'll go into that in a little while. But let's generally take something that doesn't dissociate into ions but just sort of sits there as a solid, and then it goes into a liquid. Well, maybe we want our usual picture here. Okay, so here's our picture. Now down here we have the solid A, and up here we have a solvent. And what A is going to do is equilibrate between the solid and the solvent. All right, so this is the equilibrium we're looking at. We're not worrying about dissociation or so on. Now, in order to treat this thermodynamically, we make the approximation. So if we have a solid in equilibrium with a solid in equilibrium with the compound that's solvated, what you do is approximate this as a melting. So now you have A as a liquid. So that's a pretty big approximation. We're assuming ideal solutions and everything else, but let's see what we can do if we make that approximation. So A, when it's solvated up here, well, it's just like a liquid. So A would be like in a liquid mixed in with a solvent liquid. So it would be like a liquid-liquid equilibrium. So really, thermodynamically, what controls this is the enthalpy of melting or fusion. So that's the approximation we're going to make. All right, now this is an equilibrium, so we can usually make our usual assumptions that the chemical potential of A in the solid state at equilibrium is equal to the chemical potential of A in the liquid state. We're using liquid as an approximation of solvation. Now let's go ahead and write down what the chemical potentials are for each one of these cases. So the chemical potential of A in the solid state is equal to the chemical potential of A in the solid state, standard state, plus RT times the natural log of the activity of A in the solid state. And what we said was, if we have a pure condensed phase, pure A is a solid, that's a condensed phase, the activity is then 1 because that's our standard state, and therefore this term becomes 0. So the chemical potential of something in a solid state is just, as we expect, the standard state chemical potential in the solid state. Now let's do the same thing for the chemical potential of A in the liquid state. Well, that's the standard state chemical potential of A in the liquid state, plus RT times the natural log of mole fraction of A in the liquid state. In other words, we have A here mixed in with the solvent, and what's the mole fraction of A here? That's what we mean by A in the liquid state, which is actually the solvated state, but we made that approximation. All right, so what we do is we equate these at equilibrium, and we just say that the chemical potential of A in the solid state, standard state, is the chemical potential of A in the liquid state, standard state, plus RT times the natural log of mole fraction of A in the liquid state. So you might have noticed I went from activity to mole fraction. So when I went like that, I didn't write activity here. This implies the activity coefficient of A is equal to 1. So we're making this sort of bad approximation already, so we might as well make this approximation, which may or may not be as bad. All right, so there it is. Let's isolate the natural log of XA in the liquid state. That's equal to the chemical potential of A in the solid state, standard state, minus the chemical potential of A in the liquid solid state divided by RT. Oh, so that's an interesting relation there. So where are we going here? Well, what we want to do is to look at the solubility as a function of temperature. So can we predict the solubility dependence of temperature? The answer is yes, but it's not a very good prediction, but we'll nonetheless go ahead and do that. So we want to know the temperature dependence, and this, of course, the mole fraction of A in the, as we denote liquid, is the solubility. So how much A goes into here is the mole fraction of A when this is at equilibrium. Okay, so let's see how, well, actually do one more simplification. I claim that this is minus the free energy of melting, or which is called fusion, partial molar free energy, divided by RT. Why is that? Well, the chemical potential is related to free energy, as we expect. Remember that the chemical potential is how free energy changes with the number of moles, and we give that the symbol partial free energy, partial molar free energy. And the reaction we're looking at here is solid going, here we go, solid going to liquid. So that's delta G of fusion. So be the chemical potential of the products minus that reactant, liquid minus solid. But here it's solid minus liquid. So that corresponds to the minus sign there. And then the difference in chemical potential is just delta G fusion over R. Okay, so with that, let's look at the temperature dependence, how the natural log of the mole fraction of this component in the liquid phase varies with temperature. Well, that's how, and I'll just look at G over T, okay? So this is how, and I'll put the minus sign out there, how delta G of fusion divided by temperature varies with temperature, and that's divided by R. Now remember, this is the Gibbs-Helmholtz relation. We can immediately say that this is equal to delta H of fusion. I'll put that R under there, RT squared. You might review the Gibbs-Helmholtz relation, where you can go from there to there. All right, so now let's integrate, or let's separate the terms here. So this is how natural log of the mole fraction of A in the liquid, that is equal to delta H of fusion over RT squared with the dt over here. So we're going to integrate total differential here. So let's integrate here from the melting point. Okay, so there's, or the freezing point, it's the same thing. And right at the freezing point, you have pure component A, which the mole fraction is 1, and therefore log of this. So we're going to integrate the log of this, where x is 1, from 0 to some particular value, and corresponding to that temperature. So we want to predict the temperature solubility, the temperature dependence of solubility, and we're going to reference it to the freezing point. Why is that? Well, because this is the real reaction we're approximating this reaction as. All right, so we just have on this side the natural log of the mole fraction of A in the liquid state. That's equal to, you integrate this is minus delta H fusion, and we probably should put a bar above that, give me partial molar, forgot all those, over R, 1 over T minus 1 over the freezing point. So this says that the solubility of A in a solvent is expressed as log of the mole fraction, is proportional to the enthalpy of fusion. So if it takes a lot of energy to pull apart something to melt it, then, because it's minus sign here, you're not going to get as much in solution. All right, so that's where that equation comes from. And again, the key point here is that at equilibrium, chemical potential of two things that are in equilibrium are equal. Okay. Well, let's go ahead. That's just a solid going into solution. But now let's look at solid-liquid phase equilibria. So now we have two components. It's a little different from what we had before. And again, just to clarify things, we'll draw our typical system here. We have two components. Let's call them, I don't know, 1 and 2, I guess is what we have been using. And now this is solid. And up here we have liquid. So we're not considering any vapor pressure or anything. So 1 can be in equilibrium in the solid and liquid, and 2 can be in equilibrium, the solid and liquid. And let's look at the phase diagram for this system. Okay? So, and usually what one does is look at a temperature composition graph rather than a pressure composition, because the pressure doesn't change much when you change the amounts. So temperature composition is a lot more interesting. All right, so what we'll find are these various things here, 1, 2, 3. And let's do that by looking at a particular, well, actually, no, just an example. This is an example of a liquid-solid phase diagram, or I guess I call it solid-liquid. So on the y-axis here, we have temperature, and on the x-axis, we have mole fraction. So this makes this a temperature composition phase diagram. All right, and let's look at high temperature. At high temperature, it's high enough so everything is a liquid. So in this region, we just have liquid. We have liquid A and liquid B. Okay. Now, at that high temperature, let's start at A1. Let's start cooling things down. Still have a liquid, still have a liquid. When we reach this point, what's going to happen? Something's going to freeze out, because in this region you have liquid plus solid. Let's look at, we're plotting as a mole fraction of B. So I guess in our notation this would be component 2. Should have used B. All right, so here's no component. This is pure component B. So as you hit this line, what you're going to do is to freeze out pure B, 100% B, and you're left with a liquid that has both A and B. And just let's switch our notation from 1 and 2 to A and B. So the two components are A and B, and the okay, so mole fraction B, mole fraction of A. So up here we have liquid A and B. When you hit this point, we're going to start to freeze out some pure B, and now down in here we have liquid A and liquid B, and also we have that pure. So if, for example, if we're right here at this point, what we have is solid B and a composition of liquid A and B, and we can use a lever rule. Remember the lever rule when you talked about that? This is like L1, this is length 1, this is L2, and this, by the way, the mole fraction we were using as ZB before. All right, so we can figure out what the composition of A and B are by the lever rule. And then you keep going down here, you still have liquid A, liquid B, and now at this point you freeze, and so you have another phase transition, and now you're just down here in solid. Okay? So that's what happens when you cool from this. So the key thing is here, as you're cooling more and more, you get solid, pure solid freezing out of the solution. That's a solid. And then in the liquid you have A plus B. That might be useful, for example, for purifying things, and that's exactly what you do when you do zone refining, which we'll talk about in just a minute. All right, so that's what that is. Now, what would happen if you're at this particular composition? Okay, that's a particular composition of A and B. So you're down here, you're liquid, 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 and then you just all go to solid, as opposed to here where you'd have solid plus liquid. Over here you would have solid A plus liquid A and B, and then you finally go all solid. Here it's all liquid, and then it's all solid. This particular point is called a eutectic. Eutectic. I think that's how you spell it. Eutectic point or eutectic composition. Okay, so those are important parts of the liquid-solid phase equilibrium. Pure component will freeze out from solution first. Okay, which pure component depends on where you are in the phase diagram. Solid and liquid phases are present in equilibrium. The solution is saturated. So if we go back here, right here you have solid and liquid, and it's saturated. For example, if you look at A as a solvent, B is saturated because now you have pure B being frozen out. So in this case, A is saturated with solid B. And over here on this side, here you have the liquid. So you have B, which is saturated with A because you have solid A present. Okay? And we learned about the eutectic composition. The phase transition is all solid to all liquid. All right. And an example of eutectic is solder. If you're soldering two wires together, for example, used to be tin lead eutectic, but people don't like lead anymore, so it's usually different composition. But in the old days, tin lead at a particular composition, you would just heat it up and it would melt. Interesting. And for this particular phase diagram, the eutectic here, that eutectic mixture here, melts at a lower temperature than either pure A or pure B. So solder then melts at a lower temperature than tin or lead by itself. All right, let's take an example of the use of these ideas. That's zone refining. Zone refining, well, what is that? Well, let's go to a picture. A picture's worth 1,000 words. So here we are. This is an example of zone refining. And it's used in the semiconductor industry to make very pure silicon or germanium or other things which you need to make integrated chips, and so your iPhones work really cool and they make really thin, et cetera, et cetera. Okay, so this is an example of zone refining. So over here in this area you have an impure substance. So you have mostly what you want, in this case is germanium, but it has some impurities. So you take this is a heater, and you pass the rod through the heater. Now, as the rod goes through a particular area, or as the heater goes through a particular area of this rod, what you do is you melt it. And then as you push it out, this is still melting, but now you're starting to freeze. And what freezes out first? What freezes out first is pure component. If you're over here, pure A or pure B, or in this case, pure germanium. Okay, so now you got pure germanium, and as you move this further on down, you melt, and then as it freezes out, you get the pure stuff freezing out. So this now becomes pure, 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 and the impurities are now concentrated in this molten zone. And that's very useful industrially to prepare very pure compounds for the semiconductor industry. All right, so that's it for solid-liquid phase diagrams. And now we're going to go on and talk about colligative properties.